Hello everyone, welcome to our group project on student dropout prediction in Uganda. In this video, we are going to walk you through our exploratory data analysis or EDA of a dataset containing 100,000 Ugandan school students. The goal of this project is to understand why students drop out and which factors are the strongest predictors so that one day a machine learning model can identify at-risk students early enough to help them. And we have a total of 100,000 students in the dataset, 14 features and 43.9% dropout rate and 4 regions. So what's in the dataset for starters? We have student ID, age, and gender, and these are identity fields. Then we have region, school type. Uh, these are geographic factors and maybe institutional factors. Then we have household size, household income level, and these are socioeconomic factors. Then we have parental education level, which is the family background the students may come from. We have distance to school in kilometers, so this represents the access or the geography to when going to school. And then we have attendance rate, previous exam score, which is the academic performance, has ability or orphan status, and these are the vulnerability indicators. And then dropout, which is our target variable, which is 0 or 1. We have 0 missing values, so no imputation was needed. The binary target dropout is 1 and then retained is 0. We have a 43.9% dropout rate, so it's moderately balanced with the retained. And then the gender is encoded as 1 is equal to male and 0 is equal to female. The income and education are ordinal scales of 1 to 5, and there are 4 regions considered, which is central, eastern, northern, and western. There are 2 school types, which is government, which are 75%, which are used, and private, which is 25%. So phase one, overview and target variable. I want to understand the big picture before diving into individual features. So we start off with the overview dashboard, and this dashboard is the first chart and establishes the macro picture of who is dropping out across which groups before we zoom into individual variables. So there are 4 mini charts used in one slide to save space, and it gives immediate orientation. We can see the overall dropout versus retained in that circular graph. We have dropout is 43.874 and retained is 56.126. The dropout by gender, we have red is a dropout, green is a retained. For female, we have, I think, up to slightly 2,500 were retained, and then between 2,000 and 25,000 were dropped out. And then we also have a look at dropout rate by school type and then dropout rate by region. Here is the code snippet. For the donut chart, you can see on the right, you get a data frame, a dropout value count. That's a code. Then we have the grouped bar, which is count per gender status. Again, we have data frame dot group by. Then we put the label, the gender label, the dropout label, then the size of the chart. And then we have dropout rate by school type. That's how we calculate the percentages we get. You can see for axis 1, and then we plot the bar. And the key finding was that 43.9% of students dropped out. The Western region leads dropout rates by approximately 47%. Government schools have a marginally higher dropout rate than the private schools. So we'll also have a look at the univariate analysis, and here we'll be examining each feature individually, its distribution, and the relationship it has with dropouts. Let's look at the attendance rate analysis. Here we used a box plot alongside a histogram, and it adds a statistical summary to the shape story. And together they confirm both the central tendency difference and the spread difference between dropout and retained groups. So again, you have the code snippet. You can see for label color in. So the dropout is red, retained is green, and then the values data frame, then dropout label is equal to label, which could have been set earlier, attendance rate, and then we put Seaborn for the box plot, cns.boxplot, data is equal to df, x is dropout label, y, and then the key finding was that dropouts have significantly lower attendance rates with a heavy left skewed tail. The median dropout attendance, which is approximately 0.55, is far below retained students, which is approximately 0.78, and this was the strongest visual separator in the dataset. Then we also had a violin plot, which is a box plot with a kernel density estimate embedded inside, and it shows where the data is most dense. So it's not just summary statistics, and it's ideal for showing that two groups may have similar medians but very different shapes. So this violin plot combines KDE and a box plot into one, and you can see the code of how we come up with it. We see data is equal to df, and x-axis is dropout label, y is previous exam score, and then the violin palette here was setting the colors, dropout is red and retained is green, and we have a comment that says that inner quartile draws the 25th, 50th, and 75th percentile, and the lines inside the violin body. So those quartile lines are the lines inside the violin body. And the key finding was that dropouts cluster at lower exam scores, and the violin reveals a bimodal shape for retained students, and there is a large low scoring group and a high scoring group, and this suggests even moderate performers stay enrolled most of the times. And then we also plotted a distance to school analysis against a dropout rate. So distance is continuous, but its relationship with dropout was discovered to be nonlinear. And binding it and plotting dropout rate by bin reveals threshold effects and whether risk increases gradually or jumps sharply beyond a certain distance. So once again, a code snippet of how we get the bin, and then how we calculate the dropout rate per bin, and then how we use midpoints as x-axis labels. The key finding we obtained was that the dropout risk rises with distance but is not linear, and there is a notable jump beyond approximately 15 kilometers. And we noticed that students living far from school face transport costs, safety risks, and fatigue that could compound over time. And we also had a line chart that we used together with some group bar charts, and the line chart with fill between is used for rate to is used for rate in bracket right panel to emphasize the trend direction income as continuum. The left bar chart shows row counts so we understand which income groups are represented. So we have the code again, the line chart with the shaded area for visual emphasis. So we're grouping them by household income, and then we get the dropouts, and then we add the mean times 100. And the key finding in this case was that income level 1, lowest, has approximately a 60% plus dropout rate, versus approximately 25% for level 5 highest. And this is among the steepest gradients in the entire dataset. And poverty is a dominant driver for dropout in this case. So we noticed that this caused a very steep gradient. There was a very steep increase for dropout rate as income level lowered. And this is a dominant driver for our target variable, which is dropout. And then we also plotted two side-by-side bar charts, one for counts, one for rates, to distinguish between how common is this group versus how at risk is this group. Without the count chart, a rare high-risk category might be overweight in interpretation. Below is the code, part, part of what we had. We have the edu counts, where we group by parent education and the dropout label, and then the code for coming up with the bar and the axes part of it. And the key finding was that children of parents with no education, which is level 1, face 55% plus dropout rates. Each step up in parent education consistently reduces dropout, and this confirms a strong intergenerational educational effect. So children who had parents of no education level tended to drop out more than those that had maybe parents with some education level. And then we also did some household size analysis, which is one of our variables. The household size is a count variable, so basically integers of how many people live in the house. A bar chart per value shows the exact rate for each size. The box plot on the right confirms whether the distributions of the two groups differ meaningfully in central tendency and spread. So below is the code snippet of how we got the dropout rate per household size value, and then how we came up with the box plot for distribution comparison. And the key finding was that larger households have slightly higher dropout rates, and the effect is modest but consistent. So larger families may have fewer resources per child. Maybe that's what increases the dropout pressure. And we also plotted the sort of vulnerabilities, which is disability and orphan status. These are binary categorical variables and are best compared with simple side-by-side bars. So we had two panels on one figure, which allowed direct visual comparison of two different vulnerability indicators without flipping between sides. Again, you have the code for getting the labels and setting the colors and other things that we did. And the key finding was that orphans have approximately a 55% dropout rate versus approximately 41% for non-orphans, plus 14 percentage points, and students with disabilities show similar elevated risk. These are important subgroups for targeted intervention programs. So these were also significant factors to the dropout rate, because approximately 55% dropout for orphans was a bit high, and this means these groups are very important for intervention programs to prevent students from dropping out. In this part, we're going to look at the bivariate analysis, and we're going to be exploring relationships between pairs of features and their combined effect on dropout. So what we did was we first used the correlation heat map. So why did we use a correlation heat map? The correlation heat map gives a complete pairwise overview of all numeric relationships in one chart. So it identifies multi-collinearity, that is features that are correlated with one another, and feature target correlation at a glance, and it is very essential for modeling. So we have the code of, for what we used is Pearson correlation matrix, and then we mask the upper triangle to avoid redundancy. Then we hide upper triangles. We show the number in cells. Red is positive and blue is negative, and 0 is white, which is neutral. And to the immediate left of the text, you can see the sort of ranking which is happening, and it increases from 0.05, which is the red region, and then goes up to 0.25, but in between you have the 0, which is neutral. And the key finding was that attendance rate and previous exam score have the strongest negative correlations with dropout. Household income level and parent education level also correlate negatively. So that's what we found. We found that attendance rate and previous exam score have the strongest negative correlations with dropout, but then household income level and parent education level also correlated negatively. We also plotted grouped bars to place dropout rate against region and gender. So we have these grouped bars because they allow comparison of two categorical variables simultaneously. Placing gender groups side by side within each other within each region reveals whether gender gaps are consistent or region specific. And this is impossible to see in separate charts. So having these features grouped side by side helps us to compare them, and this wouldn't be possible maybe in separate charts. So we have the code. This shows how we cross-tabulate region, gender, and then the compute rate. So then the code, we plot the kind bar on a data frame with two columns, and then this automatically creates the grouped bars. So the key finding was that northern Uganda has the highest dropout rate for both genders. Uh, Males consistently have slightly higher dropout than females in most regions, and this pattern differs from the global averages where girls typically drop out more than boys. And this was a bit strange. We also had a heat map that put dropout rate against region and school type. So why did we use a heat map? When you have two categorical variables and you want to show a certain numerical outcome for every combination, a heat map on a pivot table is more readable than grouped bars, especially when the number of combinations is small. Once again, we have the code that creates the pivot. We set the rows to region, the columns to school type, and the values as rate. The key finding was that the northern government schools have the highest dropout rate, and it was approximately 52%. Private schools outperformed government schools in every region. The region effect is larger than the school type effect. We also plotted attendance versus exam score using a scatter graph or a scatter plot. When we used a scatter plot also was that a scatter plot is the only chart that reveals a joint distribution of two continuous variables simultaneously. And we color coded them by dropout status, and this shows whether the two groups occupy distinct regions in the 2D space. So we start by setting a sample that reduces overplotting, and this is 3000 of 100,000. And the key finding was dropouts cluster in the bottom left. They cluster in the bottom left quadrant, and it's low attendance plus low score, and retained students spread across the full score range, but they tend to concentrate at higher attendance. But then these two groups again overlapped in the mid-range, and this poses a modeling challenge in future. So then we had the interaction heat map, and we use this to represent income against We use this to represent the dropout rate against income level and parent education. So this chart specifically tests for interaction effects, and it asks whether the combination of two risk factors produces worse outcomes than either alone. And the heat map is on a 5 by 5 grid and reveals exactly where the danger zones are in this particular socioeconomic landscape. So we first set the two ordinal features, and then we move on to create the graph using CNS again. And the key finding was that the worst cell, which is income, is equal to 1 and parent education is equal to 1. It has a 68% plus dropout rate and is nearly 25 points above the dataset average. The best cell, however, which was income is equal to 5 and parent education is equal to 5, sits below 20%, and the poverty trap dynamics here become clearly visible. We also had cumulative distribution functions, and a CDF answers the question of what fraction of students are below a given value. And unlike histograms, CDFs are smooth and allow precise reading. The horizontal graph between two CDF lines at any x value shows the probability a random student at that threshold is in one group or the other. So the key finding was that the CDF gap confirms that approximately 70% of dropouts have attendance rates below the 30th percentile of retained students, and that for exam scores, the gap is smaller but still significant. The low scores alone aren't as predictive as low attendance. We had another 2D heat map, and this was showing dropout rate against age and income level. So when both axes are numeric or ordinal, and we want to show a red surface, I am sure is faster than Seaborn heat map for large grids. The color surface particularly reveals whether age and income interact. So do older students in poor households face compounding risks? That's a question we wanted to answer. So we have a code that uses IMShow, and then we have IMShow treats the matrix as a 2D image. And the key finding was that students aged between 17 to 20 in income level 1 have the highest dropout rates, which was slightly greater than 70%. The interaction is significant as age alone or income alone predict less than their combination, and this confirms a possible multiplicative risk. Now, at this point, we're going to move to the multivariate analysis, and we're going to be examining 3 or more variables together to uncover complex patterns and interactions. Here, once again, we have a split violin plot that shows two group distributions side by side within a single violin shape. And here, dropout versus retained for each region. So it's a 3 variable chart, uh, which comprises of distance, region, dropout, and it's compressed into one elegant visualization. So we have the Seaborn instance of SNS.violin plot. Data is equal to df, x is equal to region, y is equal to distance to school, hue, dropout label. Those are the colors you see. Split is equal to true, so we're splitting them side by side. The comment clearly states that key merge halves into one, and then we have the drawing of the inner quartile lines, and then we have the setting of the colors. And we have comments to explain that split is equal to true is what creates the mirror halves, and without it, you'd get side by side for violin, so you would have no separator. The key finding was that northern Uganda shows the widest spread for dropouts. This was because many students travel very long distances there. The right half or dropout is consistently fatter at high distances across all regions. Then we also had a scatter matrix pair plot. A pair plot creates all pairwise scatter plots and diagonal density curves in one single call. So it's a quick way to see all bivariate relationships simultaneously, and it's very essential during EDA to spot any unexpected correlations or separation between groups. So we have the code once again, uh, and there is a comment that clearly states that sns.pairplot returns a pair grid object and not a figure. So we must access .figure for the subtitle. And the key finding was that the attendance rate and exam and previous exam score scatter, which is row 2 and column 1, shows the clearest dropout separation. Other pairs show weaker separation, and this confirms that these two features are the strongest signal sources. And we also tried to compare genders and school type against a dropout rate by using faceted bar charts. So faceting refers to splitting into subplots by a third variable, and it avoids overloading in a single chart. And by splitting government versus private schools into panels, we can compare the gender gap within each school type without these charts interfering with each other. So in the code, we loop over school types to create these facets, and then we compute rate only within this school type. And the key finding was that males have higher dropout than females in both school types, but the gap is larger in government schools, and private schools have lower overall dropout for both genders, and this suggests that maybe resource quality matters. We also had a mean value heat map, and here we plot attendance rates and attendance rates against region and school type. And while previous heat maps showed dropout rates, this heat map shows mean attendance, a continuous outcome variable, and the question it answers is attendance itself varying by region or school type, or is the variation in dropout explained by factors other than attendance management? So in the code, we first of all group by two categoricals, and we take mean of continuous variable. And the key finding was that the mean attendance rates are remarkably similar across all region school type combinations, and are all within approximately 0.66 to 0.71. And since attendance varies but dropout varies more, non-attendance factors explain much of the regional dropout differences. We also had group bar charts of three variables, and this was exam score by income and gender. And this chart answers a specific question to and this chart answers a specific question of whether gender differences in exam performance depend on income level. A group bar with income on the x-axis and gender as the group variable surfaces this three-way relationship compactly. And in the code, we start by achieving a three-way summary of income times gender to get the mean exam score. And then we have a data frame on two-column data frame. And the key finding was that exam scores rise with income for both genders. Females consistently score slightly higher than males at low income levels, and while the gap narrows at higher incomes, and this was an interesting equity finding. Then we also had a kernel density estimate, and this kernel density estimate is a smoothed histogram, and it shows the probability density of a continuous variable. So overlaying multiple kernel density estimates for each region on the same axis allows a direct comparison of score distributions without the bin-width sensitivity of histograms. So in the code, maybe what we do different is we iterate groups and plot each region's kernel density estimate. And our key finding was that all four regions show very similar score distributions, and they are nearly identical peaks around 50 to 55. And this suggests that exam performance is not strongly region dependent, and dropout differences by region come from socioeconomic and geographic factors. For the final part of our presentation, we're going to look at synthesis and predictive signals. And here we're going to be ranking features by importance and building a composite risk model. So here we had a horizontal bar chart which was ranked. So why we used a ranked horizontal bar chart of correlations is because it acts as a simple feature importance proxy before formal modeling. And the color coding by direction, positive versus negative correlation, makes interpretation instant. These horizontal bars give space for long features. And below is the code of what we did different from other graphs. And the key finding was that attendance rate is the strongest negative predictor, and previous exam score is second. Distance to school in kilometers and orphan status are the strongest positive predictors of dropout. We also had a dual axis line plus bar chart to compare dropout rate by composite risk score, which was from 0 to 7. A composite score is a form of EDA storytelling, and it synthesizes all findings into one interpretable number. And we had a dual axis chart, sometimes called a twinks, and it overlays the dropout rate trend on the student count distribution, showing both how at risk and how many students live at each. So in the code, we try to engineer a risk score, and we sum 7 binary risk flags, and then we come up with a dual axis, and this creates a second y-axis. The key finding was that students with 0 risk factors have approximately 10% dropout, and students with 7 risk factors have approximately 98% dropout. And this near perfect gradient confirms that risk factors are not redundant, and each one adds independent and predictive power. So the key takeaways, what does this EDA tell us? Number one is that attendance is the number one predictor, and dropout and retained students are most separated by attendance rates. And this was the single strongest Pearson correlation with the target variable. The second thing was that poverty compounds all other risks. So we have low income plus low parent education creates a 65% plus dropout hotspot. And socioeconomic factors don't act alone, they amplify every other risk. And the third thing was that vulnerability stacks exponentially, and students with 4 plus risk factors from the composite score face a near certain dropout rate, which was greater than 90%. Orphan plus disability combinations are especially critical for this. And the last and fourth thing was that geography still matters, and northern Uganda had the highest dropout rates. And that means that distance to school is a meaningful barrier, especially for girls in rural government schools. So that has been our presentation, and thank you very much for listening.